Tonight, we're going to explore one of the strangest contradictions in all of space exploration. Voyager 1 launched on the 5th of September 1977. It is the most distant human-made object ever built. It crossed the heliopause in August 2012, becoming the first human object to enter interstellar space. It is racing outward at roughly 38,000 miles per hour, or about 61,000 kilometers per hour, and by the year 3000 more than 1,000 years will have passed since its launch. Given numbers like that, Voyager should feel unimaginably far away by then. 1,000 years sounds like enough time for a spacecraft to vanish into some truly remote part of the galaxy. It sounds like enough time to approach another star, or at least to leave the sun's realm behind in a way that feels final. 1,000 years is longer than the time between us and the Norman conquest of England, longer than the rise and fall of entire dynasties, long enough for kingdoms to disappear, coastlines to shift, religions to spread, and languages to split into new ones. And yet the deeper reality is far more unsettling. By the year 3000, Voyager 1 will still be near the beginning of the journey people usually imagine when they picture it drifting into the stars. That is the contradiction at the center of this story. Voyager is one of the most admired machines humanity has ever built. It visited Jupiter in 1979 and Saturn in 1980. It revealed volcanoes erupting on Io, gave us extraordinary close views of Saturn's rings, and helped turn the outer solar system from a collection of distant lights into a place of real worlds, real weather, and real landscapes. It also carries the golden record, a 12-inch gold-plated disc filled with sounds, images, greetings, and music from Earth. Over time, that record gave Voyager a larger symbolic weight. It stopped feeling like a spacecraft that completed one mission and kept moving outward. It started to feel like humanity's first true emissary to the stars. That idea has power. It deserves some of its power. But the scale behind it is harsher than most people realize. The region Voyager entered in 2012 is often described in a way that sounds final: interstellar space. The phrase has enormous dramatic weight. It sounds like a clean crossing, a grand departure, a line between the solar system and the wider galaxy. But the solar system, in the deeper gravitational sense, stretches far beyond the planets, far beyond Pluto, and far beyond the heliopause. Out there lies the Oort Cloud, a vast spherical region of icy debris left over from the formation of the solar system. Its inner edge may begin around 2,000 astronomical units from the Sun. Its outer edge may extend to 100,000 astronomical units, roughly 1.5 to 2 light-years away. Voyager 1 is nowhere near that far. At its current speed, it will take roughly 300 years just to reach the inner edge of the Oort Cloud. Passing through that distant region could take around 30,000 years more. That means the year 3000, a date that sounds almost absurdly distant on a human scale, places Voyager near the beginning of the Sun's true far frontier rather than anywhere close to the end of it. That changes the emotional shape of the mission. Once you see those numbers clearly, Voyager starts to look different. Its outward motion remains real. Its achievements remain extraordinary. But the romantic picture many people carry begins to shift. 1,000 years starts to feel less like a completion and more like a tiny movement against an almost impossible backdrop. The spacecraft keeps going. The calendar surges forward. Human history keeps piling up behind it. and the actual physical change in Voyager's larger situation stays disturbingly small. There is one more detail that sharpens the contradiction. Voyager's radioisotope power source has been fading for decades. NASA has already been shutting down instruments one by one to conserve electricity. Sometime in the late 2030s or early 2040s, Voyager will fall silent. Long before the year 3000 arrives, the mission as a living exchange between humanity and the spacecraft will already be over. No more data, no more signals. The probe will continue outward as a cold, dark artifact moving through a region so large that even 1,000 years barely changes the picture. And that is why this question matters. Voyager is often treated as one of humanity's boldest first steps into interstellar space. A heroic machine, a scientific triumph, a message to the cosmos. All of that is true. But once you confront where Voyager will actually be in the year 3000, another possibility starts to take shape. The distance between the legend and the physical reality becomes hard to ignore. To see why, we need to begin with the picture most people already carry when they hear the name Voyager. Voyager 1 does not live in most people's heads as a piece of hardware. It lives there as an idea. It is the spacecraft that escaped. The spacecraft that kept going. The spacecraft carrying Earth out into the dark. That image is powerful because it pulls together several different stories and makes them feel like one single thing. There is the real mission. There is the golden record. There is the phrase interstellar space. And there is the simple emotional fact that Voyager is farther away than anything else we have ever built. Once those pieces combine, Voyager stops feeling like an aging machine launched in the 1970s. It starts to feel like humanity's first true voyage to the stars. That is the version people remember. It is the version that shows up in documentaries, classroom posters, news headlines, and quiet, late-night thoughts about the future. Voyager becomes a symbol of endurance, a symbol of ambition, a symbol of the hope that something from Earth can keep moving long after the people who launched it are gone. The golden record plays a huge part in that transformation. In 1977, NASA attached a 1-2-inch gold-plated copper disc to each Voyager spacecraft. The record carried greetings in 55 languages. It carried music by Bach, Beethoven, Chuck Berry, and traditional performers from several parts of the world. It carried sounds from Earth, including wind, thunder, birds, footsteps, laughter, and a baby crying. It also carried images encoded into analog signals, pictures of human beings, animals, landscapes, scientific diagrams, and the structure of DNA. Those details matter because they changed the emotional meaning of the mission. A probe sent to study planets is one kind of object. A probe carrying a record from Earth feels like something else entirely. It feels almost ceremonial, almost poetic, almost like a bottle dropped into an ocean too large for language. Then there is the phrase interstellar space. That phrase gives Voyager a second layer of legend. When NASA announced in 2013 that Voyager 1 had crossed the heliopause in August 2012, it sounded to many people like a final departure from the solar system. The heliopause is the region where the solar wind, the stream of charged particles flowing outward from the sun, weakens enough for the interstellar medium to dominate. The interstellar medium is the thin gas and dust that exists between stars. Crossing that boundary was real. It was historic. But emotionally, The phrase did more than describe a scientific milestone. It made Voyager sound like a starship. Add that to the golden record, and the public picture becomes almost irresistible. Voyager is no longer only the spacecraft that flew past Jupiter in 1979 and Saturn in 1980. It becomes the machine carrying our species outward, the machine bearing our voice, the machine already on its way to wherever comes next. That is where the myth begins to harden. And myths are not useless. Sometimes they preserve something real. Voyager really was extraordinary. It really did survive, far beyond its original expected lifetime. It really did become the most distant human-made object in existence. It really is still moving outward through darkness that no human being will ever physically follow in person. But the legend smooths over important edges. It compresses a planetary science mission, a cultural time capsule, a historic boundary crossing, and a deep emotional symbol into one seamless story. That seamless story is satisfying. It is also dangerous if we want to think clearly about what Voyager actually is. Because once a machine becomes a legend, scale begins to blur. Purpose begins to blur. Distance begins to blur. A spacecraft that studied Jupiter's storms, Saturn's rings, Titan's atmosphere, and Io's volcanoes starts to feel as if it was always meant for the stars. A silent record attached to aluminum and titanium starts to feel like an active conversation with the galaxy. A probe moving at tens of thousands of miles per hour starts to feel faster than it really is. That is why the legend has to be separated from the machine. Not to strip away the beauty, to see what kind of beauty this really is. And to do that, we have to go back to the beginning, before Voyager became a symbol, and remember what it was actually built to do. To see Voyager clearly, it helps to place it back in the 1970s, before the legend hardened around it. The mission did not begin as a romantic attempt to reach another star. It began as a very practical chance to study the outer planets up close. In the late 1960s, mission planners realized that Jupiter, Saturn, Uranus, and Neptune were moving into a rare alignment. That alignment meant a spacecraft could use one planet's gravity to bend its path and gain speed toward the next one. A gravity assist is exactly what it sounds like. The spacecraft falls into a planet's gravity well, swings around it, and leaves on a new path with extra velocity. That opportunity does not happen on a humanly convenient schedule. For the 4 outer giant planets to line up in a way that supports a multi-planet tour, you wait about 176 years. NASA decided to use that opening. The original project was called Mariner Jupiter-Saturn 1977. Later, it became Voyager 1 and Voyager 2. Voyager 1 launched on the 5th of September 1977 from Cape Canaveral in Florida. Voyager 2 actually launched first, on the 20th of August 1977. But Voyager 1 was given the faster path. That faster path let it arrive at Jupiter and Saturn sooner. The probe itself weighed about 825 kilograms, or roughly 1,820 pounds. It carried cameras, spectrometers, magnetometers, plasma instruments, and particle detectors. Those tools were built to answer concrete questions about real worlds. What are Jupiter's cloud bands made of? How strong is its magnetic field? What is happening on the surfaces of its moons? How thick is Titan's atmosphere? What are Saturn's rings actually like when viewed close up? That was the mission. not to drift aimlessly outward in the hope of finding something someday, not to deliver a practical message to another civilization, not to travel directly to another star. Voyager 1 reached Jupiter on the 5th of March, 1979. It gave scientists their first detailed, close views of the Great Red Spot, lightning in Jupiter's atmosphere, and the violent volcanic eruptions on Io. Io turned out to be the most volcanically active body in the solar system. That discovery alone changed planetary science. Then Voyager 1 reached Saturn. On the 12th of November 1980, it returned extraordinary images of the rings, their fine structure, and the shepherd moons that help shape them. It also made a close flyby of Titan, Saturn's largest moon. Titan mattered because it has a thick nitrogen atmosphere, something no other moon was known to have. That flyby was so important that it shaped Voyager 1's entire future. To pass close enough to Titan for meaningful science, Voyager 1 had to take a particular path past Saturn. That path bent the spacecraft northward, out of the flat plane where most planets orbit. That plane is called the ecliptic. Once Voyager 1 left Saturn on that trajectory, it could no longer continue onward to Uranus and Neptune. Voyager 2 took the slower route and became the spacecraft that visited those planets instead. So, Voyager 1's long future beyond Saturn did not come from a carefully chosen, star-bound destination. It came from a successful planetary mission whose final turn happened to aim it outward. Its later role as an interstellar symbol grew from geometry, timing, and durability. The hardware survived. The power source kept working. The trajectory carried it beyond the giant planets. And because it kept going, people began to read a larger meaning into that motion. That larger meaning is understandable, but it can also blur the original purpose. Voyager was built first to investigate Jupiter and Saturn as physical places, with measurable atmospheres, rings, radiation belts, and moons. Only after that success did its outward drift begin to feel like a statement about humanity itself. And once a mission built for planetary science becomes a symbol of our future among the stars, it becomes much easier to let the symbol grow larger than the mission that launched it. None of this means Voyager failed. In the part of the mission it was actually built to carry out, Voyager 1 was one of the great successes in the history of exploration. When it reached Jupiter in March 1979, it did not send back minor refinements to what astronomers already knew. It changed the picture completely. Jupiter had been a bright, striped disk in telescopes for centuries. Voyager showed those stripes as active weather bands wrapped around a world 88,846 miles wide, with storms, turbulence, lightning, and a magnetic environment far more violent than most people had imagined. The Great Red Spot was no longer just a famous red oval. It became a real atmospheric system, larger than Earth, rotating inside an atmosphere full of layered cloud belts and jet streams. Voyager also found lightning in Jupiter's atmosphere. That mattered because lightning points to violent convective weather, the kind of vertical churning that moves heat and material through a planet's upper clouds. Then came the moons. Io, the innermost of the 4 large Galilean moons, turned out to be covered in active volcanoes. Before Voyager, no one had seen active volcanism anywhere beyond Earth. Then a plume was spotted rising about 186 miles above Io's surface. That single discovery changed planetary science because it showed that distant moons could be geologically alive. Europa looked different in another way. Its surface was smooth, bright, and crossed by long, dark cracks. That pattern suggested the ice might be floating over a hidden ocean, which is one reason Europa is still treated as one of the most promising places to search for life in the solar system. Ganymede and Callisto added their own story. Both looked ancient and heavily cratered, preserving a record of impacts from the early solar system. So even before Voyager reached Saturn, it had already done something extraordinary. It had taken what looked from Earth like points of light and turned them into individual worlds with different histories, surfaces, and internal activity. Then it reached Saturn in November 1980 and did it again. Saturn's rings had always looked elegant from a distance. Voyager showed that elegance was built from chaos on a tiny scale. The rings were not smooth, solid bands. They were made of countless particles, mostly water ice, ranging from grains to chunks the size of houses. They stretched tens of thousands of miles across and remained astonishingly thin, in some places only about 33 feet thick. Voyager also showed ringlets, gaps, waves, and fine structure shaped by gravity. Some of that structure came from shepherd moons, small moons, whose gravity helps keep ring material confined. That was not just beautiful. It was dynamic. It showed Saturn's rings as an active mechanical system, not a decorative feature. Titan made the flyby even more important. Voyager 1 passed close enough to reveal that Titan has a thick atmosphere made mostly of nitrogen, with methane mixed in. Nitrogen is the main gas in Earth's atmosphere too, so Titan immediately became more than just another moon. It became a place with weather, chemistry, and a physical environment worth taking seriously. The surface stayed hidden beneath orange haze. But the atmosphere alone made Titan one of the most intriguing objects in the outer solar system. Jupiter had also shown Voyager something harsher. Its magnetic field was immense, and its radiation belts were so intense that they threatened spacecraft electronics. Saturn's magnetic environment was weaker, but still powerful. So Voyager did more than collect pretty images. It measured charged particles, plasma, and magnetic fields around giant planets whose environments could strip, heat, bend, or trap matter in ways impossible to study properly from Earth. That is why it would be wrong to treat this script as an attack on Voyager itself. Voyager 1 was a scientific triumph. It did exactly what a great exploration mission is supposed to do. It went somewhere difficult. It observed with precision. It surprised the people who built it. It made the solar system feel larger, stranger, and more alive. The tension enters later, not in what Voyager accomplished at Jupiter and Saturn. The tension begins after all of that. Once the flybys were done, once the cameras looked back across a completed planetary mission, and once a spacecraft built for close-up science kept moving into darkness long enough for people to give that motion a much larger meaning. Because if Voyager succeeded this brilliantly at the mission it was built to perform, why does the shape of its future still feel so unsettling? This is the version of Voyager most people carry without even realizing it. The spacecraft has already left the planets behind. It crossed into interstellar space in 2012. It carries a golden record filled with sounds from Earth. It is farther away than anything else humans have ever made. Put those facts together, and the story almost writes itself. Voyager becomes the first real traveler between the stars. It becomes the machine carrying humanity outward. It becomes a small ambassador moving steadily towards some future moment of discovery, contact, or recognition. That picture is easy to understand because every part of it feels emotionally clean. The probe left Earth in 1977. It survived Jupiter in 1979. It survived Saturn in 1980. It kept going after the science mission was over. It crossed a major boundary more than 3 decades later. It carries music, greetings, and images from this planet. There is a beginning. There is endurance. There is a message. There is darkness ahead. That feels like a story with direction. And once a story has direction, the human mind wants a destination. The golden record strengthens that feeling more than almost anything else. A spacecraft carrying cameras and particle detectors feels technical. A spacecraft carrying Bach, Chuck Berry, whale sounds, a baby crying, and greetings in 55 languages feels personal. It feels intentional in a deeper way. It feels as though the mission was not only built to study Jupiter's cloud bands or Saturn's rings, but to represent us. That is where the emotional blending happens. Scientific mission becomes cultural symbol. A surviving probe becomes a Voyager in the more literary sense. Motion becomes meaning. The word Voyager itself helps. NASA did not call these spacecraft Probe 1 and Probe 2. It called them Voyager 1 and Voyager 2. That name matters. A Voyager is not just an instrument. A Voyager is someone or something on a journey. Something leaving the known world behind. Something heading into distance with purpose. So even people who know the basic facts can start to absorb a larger one without noticing. Voyager is moving away from Earth. Therefore, it must be moving towards something. That idea becomes even stronger once the spacecraft falls silent in our imagination. A dead probe drifting in darkness should feel cold and empty. Instead, people often picture it as noble, still carrying Earth, still bearing its golden record, still traveling towards some unimaginable future. That is not irrational. It is how humans make emotional sense of motion through time. We do it with explorers. We do it with ships. We do it with tombs, ruins, and messages left behind by people who knew they would not see the end of the story. We turn survival into intention. We turn continuation into destiny. And in Voyager's case, that instinct becomes especially strong because space itself helps create the illusion. Out beyond Saturn, there are no familiar landmarks. No mountains, no coastlines, no visible road. There is only outward motion against black distance. Once the planets are gone, the imagination fills in the rest. It tells us Voyager must be on its way to the stars in some meaningful sense. It tells us the golden record must be part of a future encounter. It tells us a machine that has gone this far must eventually arrive somewhere that justifies the journey. That is the story we keep telling ourselves. It is satisfying because it turns drift into destination. It turns survival into progress. It turns a silent machine into a continuing act of human reach. But that whole story rests on one assumption that sounds obvious until you stop and examine it. It assumes Voyager is moving fast enough for that picture to make sense at all. Voyager 1 is moving at about 38,000 miles per hour, or roughly 17 kilometers per second, relative to our star. That speed is hard for a human body to picture. At 38,000 miles per hour, you could travel from New York to Los Angeles in well under 10 minutes. You could circle Earth at the equator in less than 16 hours. You could go from Earth to the Moon, an average distance of about 238,900 miles, in a little over 6 hours if you could move in a straight line at that pace. By the standards of aircraft, artillery, cars, ships, or anything built for daily life, Voyager is absurdly fast. Even by spacecraft standards, it is exceptional. When Voyager 1 left Saturn in 1980, it became one of the fastest objects humanity had ever sent away from Earth. That is why the mission feels so powerful in the imagination. A machine moving that quickly sounds as if it must be truly leaving. And on the scale of the inner solar system, that feeling makes sense. Jupiter orbits at an average distance of about 484 million miles from Earth at closest broad comparison. Saturn is much farther. Voyager reached Jupiter in about a year and a half after launch. It reached Saturn in about 3 years. Those are long missions by human patience, yet still short enough to fit inside one working life. That is the scale our instincts were built to understand. Months, years, maybe decades. Once the distances stay within the planetary neighborhood, 38,000 miles per hour still feels like progress. But the feeling changes the moment the target is no longer a planet. The nearest star system beyond our own is Alpha Centauri. Its closest member to us, Proxima Centauri, is about 4.24 light-years away. 1 light-year is the distance light travels in a year, about 5.88 trillion miles. So 4.24 light-years is almost 25 trillion miles. That number is large enough to become meaningless unless you force it back into time. At Voyager 1's current speed, a trip of about 25 trillion miles would take roughly 73,000 to 74,000 years. That is not a poetic exaggeration. That is the harsh arithmetic of dividing interstellar distance by a very fast spacecraft that is still nowhere near the speed of light. Human civilization has not existed in its current form for that long. Agriculture began around 10,000 to 12,000 years ago. The pyramids at Giza are about 4,500 years old. The Roman Empire in the West lasted roughly 500 years. Voyager, moving faster than almost anything we have ever launched, would still need a span many times longer than recorded history to reach the nearest star. That is the scale correction the imagination resists. Because 38,000 miles per hour sounds like escape. It sounds like departure. It sounds like the machine must already be far into some meaningful interstellar future. But in the context that matters here, Voyager is moving at about 0.0057% of the speed of light. Light travels around 186,282 miles per second. Voyager moves about 10.5 miles per second. That difference is so extreme that both numbers almost stop feeling as though they belong to the same universe. And that is why the year 3000 can be emotionally misleading. 1,000 years sounds enormous because human history is short. 1,000 years is enough time for nations to rise, fragment, disappear, and be replaced. It is enough time for one language to become several. It is enough time for coastlines, forests, and cities to change beyond recognition. But 1,000 years multiplied by Voyager's present speed still does not buy very much once the distances stop being planetary and start becoming interstellar. The spacecraft keeps moving. The calendar keeps advancing. The emotional picture keeps telling us that something major must have happened by then. Speed is the first place where that picture begins to break. Because once you stop hearing the number as a thrill and start treating it as distance over time, the real shape of Voyager's future becomes much harder, much slower, and much smaller than the legend suggests. So what does that speed actually purchase by the year 3000? If Voyager 1 keeps moving at roughly its present speed, then by the year 3000 it will have traveled about 333 billion miles after launch. That sounds enormous. It is enormous on a human scale. It is more than 1,000. 300 times the average distance from Earth to the Moon. It is far beyond the orbits of Jupiter, Saturn, Uranus, Neptune, and Pluto. It is a number large enough to make almost any ordinary journey feel finished several million times over. But this is where the emotional illusion breaks apart. 333 billion miles is still a very small number compared with the distances people imagine when they hear words like interstellar, starbound, or cosmic voyage. One astronomical unit is the average distance between Earth and our star, about 93 million miles. Voyager 1 is already more than 160 astronomical units away. By the year 3000, it would be only a few thousand astronomical units from where it started. That is nowhere near another star. It is nowhere near a planet we hope to visit. It is nowhere near a future moment of contact. It is not even the kind of distance where a new destination comes into view. In fact, year 3000 places Voyager in a region that is still more closely tied to our own system than the public image usually admits. This is the first real shock. The calendar changes much more dramatically than the spacecraft's practical situation. 1,000 years pass. Governments vanish. Cities are buried and rebuilt. Languages drift so far that modern English would sound ancient and broken. The distance from the year 1000 to today includes Viking expansion, the Song dynasty, the Crusades, the Black Death, the fall of Constantinople, the Renaissance, the Industrial Revolution, electricity, radio, airplanes, nuclear weapons, computers, and spaceflight. That is how much history fits inside 1,000 years. And during an equally long stretch into the future, Voyager still does not arrive anywhere that feels like a true interstellar destination. That does not make the spacecraft unimpressive. It makes space harder than our instincts allow. There is also a second layer to the shock. Most people hear a number like 333 billion miles and assume the story must have moved on to a different chapter. Surely by then Voyager is no longer part of our own distant neighborhood. Surely by then the probe has crossed into some truly separate realm. But that depends on where you think the edge of our system really is. If you use the outer planets as the map, then yes, Voyager is already far beyond them. If you use the heliopause, the boundary where the solar wind gives way to the interstellar medium, then Voyager crossed that in 2012. But if you use the larger gravitational map, the one that includes the Oort Cloud, then the picture changes. The Oort Cloud is not a neat shell with a visible surface. It is a vast, sparse swarm of icy bodies left over from the formation of the solar system. Comets in that distant region can take thousands or even millions of years to complete one orbit. The inner edge is often placed around 2,000 astronomical units. The outer edge may extend tens of thousands of astronomical units farther. By the year 3000, Voyager is still in the early part of that story, still close to home by the standards that matter here, still inside a scale so large that human history barely makes a dent in it. That is why the year 3000 feels so strange once you stop hearing it as a date and start hearing it as a distance. The date sounds final. The distance sounds unfinished. The mythology around Voyager tells us that time and motion should have turned this into a grand outward crossing by then. The arithmetic says something colder. It says that 1,000 years of human expectation buys far less physical progress than the legend suggests. And that contrast only becomes fully brutal once we stop pretending the planets were ever the real edge of the map. For many people, the solar system ends with the last familiar planet. Maybe that edge is Neptune, orbiting at an average distance of about 2.8 billion miles from our star. Maybe it is Pluto, once taught as the 9th planet, orbiting about 3.7 billion miles away on average, though its path is stretched and tilted compared with the major planets. That picture is understandable. The planets are what show up on classroom charts. The planets are what appear in museum models. The planets are the named places most people can point to on a map of space. So once a spacecraft moves beyond Pluto, it feels as though it has crossed the border into somewhere else entirely. That is part of the reason Voyager sounds farther along than it really is. By the early 1990s, Voyager had already passed the giant planets. By the time Pluto was reclassified as a dwarf planet in 2006, Voyager 1 was already deep beyond that region, and in August 2012, Voyager crossed another boundary with an even more dramatic name. It crossed the heliopause. That sounds final. It sounds like a wall. It sounds like the point where the solar system ends and true interstellar space begins. But the heliopause is not the end of everything tied to our star. It is the edge of the heliosphere. The heliosphere is the large bubble formed by the solar wind, which is the stream of charged particles flowing outward from our star at hundreds of miles per second. Inside that bubble, the solar wind still dominates the local environment. Outside that bubble, the interstellar medium becomes stronger. The interstellar medium is the thin gas and dust spread between stars. So when Voyager crossed the heliopause in 2012, it did enter interstellar space in that physical sense. That milestone was real. It was historic. It meant Voyager had moved beyond the region where the solar wind still controlled the local particle environment. But that did not mean Voyager had escaped the larger domain of our star's gravity. That is the part people usually miss. The sun's light fades quickly with distance. Its solar wind also weakens and eventually gives way. Its gravity is different. Gravity keeps reaching. It becomes weaker and weaker with distance, but it does not stop at Neptune, Pluto, or even the heliopause. And once that larger map enters the story, the outer solar system gets much bigger than most people imagine. Far beyond the planets lies the Oort Cloud. The Oort Cloud is not a ring like Saturn's rings. It is not a flat belt like the main asteroid belt between Mars and Jupiter. It is thought to be a huge, roughly spherical swarm of icy bodies surrounding the solar system in every direction. These objects are leftovers from the early formation of the planets about 4.5 billion years ago. Some were scattered outward by the gravity of Jupiter, Saturn, Uranus, and Neptune. Instead of being thrown completely free, many ended up in extremely long, distant orbits. That distant reservoir is what astronomers call the Oort Cloud. The inner edge is often placed around 2,000 astronomical units. 1 astronomical unit is the average distance from Earth to our star, about 93 million miles. So 2,000 astronomical units is about 186 billion miles. The outer edge may extend as far as 100,000 astronomical units. That is around 9.3 trillion miles. At that scale, you are no longer talking about a tidy collection of planets. You are talking about a deep, frozen shell of debris that may stretch nearly 1.5 to 2 light-years from our star in every direction. That is the map Voyager has to be measured against. And once you use that map instead of the planetary one, the emotional meaning of its journey changes immediately. Because Voyager did not leave the planets and head into some empty space where our system was finished. Voyager left the planets and entered a much larger, much quieter, much more thinly populated outer realm that still belongs, in the deeper gravitational sense, to the same stellar family. This is why the year 3000 turns out to be harsher than it first sounds. If the solar system ended near Pluto, then 1,000 years of further travel would feel like a vast heroic surplus. But if the real outer structure is the Oort Cloud, then Voyager is still dealing with the outskirts of home. And once that becomes the frame, the year 3000 picture starts to look much smaller than the legend suggests. Once the Oort Cloud becomes the map, the year 3000 stops feeling grand and starts feeling painfully early. Voyager 1 is moving outward at about 17 kilometers per second, or roughly 38,000 miles per hour. That is fast enough to cross the continental United States in about 6 minutes. It is fast enough to reach the moon in a little over 6 hours if the path was straight and nothing got in the way. It is nowhere near fast enough to make the outer frontier feel small. The inner edge of the Oort Cloud is often placed around 2,000 astronomical units from our star. An astronomical unit is the average distance between Earth and our star, about 93 million miles. So 2,000 astronomical units works out to roughly 186 billion miles. Voyager launched in 1977. If it keeps moving at roughly its present speed, it reaches that inner edge only around the late 2200s or the 2300s, roughly 300 years after launch. That means the first serious encounter with the Sun's farthest debris field happens on a timescale longer than the entire history of the United States. It happens on a timescale that stretches from the age of muskets and sailing ships to a future farther from us than the year 1700 was from the builders of Stonehenge. And that is only the beginning. The Oort Cloud is not a wall. It is not a checkpoint. It is a vast three-dimensional swarm of icy bodies spread thinly across distances so large that even a spacecraft moving non-stop for millennia barely changes the picture. Its outer boundary may extend to around 100,000 astronomical units. That is about 9.3 trillion miles. It is roughly 1.5 light-years from our star, and some estimates push it closer to 2 light-years. Voyager does not cross that enormous region in a heroic final burst. It drifts through it for about 30,000 years. That is the scale correction most people never make. By the year 3000, Voyager is not finishing the outer frontier. It is not even close. By then, more than 1,000 years have passed on Earth. Empires could rise, fracture, and vanish several times over. The English spoken now could become as distant from future speech as Old English is from us today. Major coastlines may shift through erosion, sea level change, and tectonic motion. Entire religions could split into branches we would not recognize. Political maps could be redrawn 100 times. And all the while, Voyager would still be near the beginning of a region that remains gravitationally tied to the same star system where it was built. That is what makes the year 3000 idea so emotionally deceptive? The date sounds final because human civilization is short. The distance stays unfinished because the solar system, properly understood, is immense. If the mission launched in 1977, then the year 3000 arrives after about 1023 years of travel. That sounds like enough time for closure. On the real map, it is closer to the opening stretch of the farthest chapter. It also changes the feel of the word interstellar. Voyager is in interstellar space in the particle physics sense, because it moved beyond the heliopause in 2012. But it is still bound up with the solar system's larger structure in the gravitational sense. That difference matters. Without it, the story sounds like escape. With it, the story sounds like endurance. And endurance is slower, much slower. The farther out you push the true boundary, the smaller human milestones start to look. A century shrinks. A millennium shrinks. Even 10,000 years starts to feel less like a grand future and more like an early interval in a process that barely notices us. That is the real outer frontier Voyager entered. Not a clear road toward another star. A dim, frozen, drawn-out region of comets, ice, and scattered remnants, so wide that even 30,000 years only just carries a machine across it. And if that is the journey still ahead, then what exactly will Voyager be by the time it is making it? There is another reason the year 3000 feels emotionally misleading. Voyager 1 may still be moving then, but the mission people imagine will be over long before that date arrives. At launch in September 1977, Voyager's radioisotope thermoelectric generator, usually shortened to RTG, produced about 470 watts of electrical power. That is not much by modern standards. A small microwave oven uses more than that. A household hairdryer often uses 2 or 3 times as much. And yet, those 470 watts had to run the spacecraft's computers, scientific instruments, heaters, radio systems, and control electronics in deep space. The RTG works by using plutonium-238, a radioactive material that gives off heat as it decays. That heat is converted into electricity. The process is reliable, which is one reason Voyager lasted so long, but it is not permanent. Plutonium-238 has a half-life of 87.7 years. A half-life means the time required for half of the original radioactive material to decay, so the power does not suddenly crash all at once. It falls slowly, year after year, decade after decade, like a battery that can last for generations but never recharge. That slow decline shaped everything NASA did with Voyager in later years. Engineers had to begin shutting systems down one by one to preserve the parts that mattered most. The cameras were turned off in 1990 after the family portrait sequence, which included the famous pale blue dot image taken from about 3.7 billion miles away. They were no longer useful in the darkness that lay ahead. As the years passed, other instruments were also powered down. Heaters were cut where possible. Backup systems were sacrificed. Every watt became precious. This is what makes the year 3000 framing so harsh. The date sounds vast. The active mission is not vast. The active mission ends on a timescale that fits comfortably inside ordinary family memory. Someone born in the late 1990s could still live to see the last years of Voyager's voice if they reach old age. Children alive now may still be alive when the final signal is received. That is the real scale of the ending. Not the distant medieval-looking grandeur of the year 3000. Something much nearer. Something almost local in emotional terms. NASA expects Voyager 1 to go silent in the late 2030s or early 2040s, when there will no longer be enough electricity to run instruments and maintain communication. That means the spacecraft's useful scientific life likely ends roughly 60 to 70 years after the 1977 launch. That is an extraordinary engineering achievement. Very few machines built by human hands have remained functional that long while moving through radiation, cold, and near-total isolation. But it is also tiny compared with the distances people project onto Voyager's future. By the time the probe reaches the year 3000, it will have been silent for nearly 1,000 years. By the time it reaches the inner edge of the Oort Cloud, the spacecraft will already have been dead for centuries. By the time it finishes crossing that huge outer debris field, if it ever can be said to finish such a crossing, the machine's last transmission will be older than the Roman Republic is to us today. That comparison changes the emotional picture. We often speak of Voyager as though it is still carrying out a long mission. In a physical sense, it is still traveling. In a practical sense, the mission becomes a relic very soon. No more measurements of plasma, no more readings of magnetic fields, no more engineering updates, no more small corrections from teams on Earth, no voice returning across billions of miles. That turns the spacecraft into something very different. A working probe is an exchange. A silent probe is an object. Before silence, Voyager is still part of a relationship between human beings and the machine. After silence, it becomes a drifting artifact, still moving, still real, still astonishing, but no longer participating. And once that happens, the meaning of the journey begins to change. It stops feeling like an ongoing act of exploration in the ordinary sense. It starts to feel more like a relic from an earlier age, continuing outward without us, carrying the memory of a mission long after the mission itself has ended. That shift matters, because once Voyager goes silent, it is no longer enough to ask where it will be. We also have to ask, what kind of thing will still be making that journey? After the final transmission, Voyager 1 keeps moving outward on the same broad path. Its speed stays real. Its distance keeps growing. Its age keeps increasing. But the nature of the journey changes completely. Up to that final stage, Voyager is still part of a living exchange. Engineers on Earth send commands through NASA's Deep Space Network, a set of giant radio antennas in California, Spain, and Australia. Voyager receives those commands, adjusts its systems, and sends data back across billions of miles. That is what makes it a functioning spacecraft. It still participates. It still answers. It still belongs to an active relationship between human beings and a machine. Once that exchange ends, Voyager becomes something else. The 3-7-meter high-gain antenna will still be attached to the body. The long booms carrying instruments will still stretch outward. The gold-plated record will still be bolted to the side. The aluminum and titanium frame will still be there. But a machine that cannot send measurements, receive instructions, or turn its surviving systems toward Earth has crossed into a different category. It has become a relic. That word matters. A relic is not just something old. It is something left over from a completed age. Voyager will still be physically present. It will still be moving at roughly 17 kilometers per second, but motion by itself is not the same as exploration. A functioning probe explores because it can detect, record, and return. A silent probe simply continues. That difference is easy to miss because the language around Voyager stays romantic. People say it is still traveling. They say it is still heading outward. They say it is still carrying Earth into the depths of space. All of that is true in a literal sense. The craft will keep going for thousands, perhaps millions of years, unless some future collision changes its fate. But the active mission ends on an ordinary human timeline, around the late 2030s or early 2040s. After that, Voyager becomes closer to an ancient arrow than a living instrument. The arrow still flies for a while after it leaves the bow. The flight is real. The guidance is over. That is what makes the year 3000 feel stranger than it first appears. When people imagine Voyager in the year 3000, they often imagine an ongoing mission stretched across a larger calendar. The reality is quieter. By then, the last engineers who touched the spacecraft by radio will have been gone for centuries. The final data packet will be ancient history. Its last working instruments will have fallen silent almost 1,000 years earlier. No one will be listening to fresh reports from that machine. No new measurement of plasma. No new reading of cosmic rays. No status check from the onboard computers. The craft will still exist, but as an object detached from any continuing human conversation. That silence also changes the emotional meaning of distance. 1 billion more miles feels different when the machine can still tell us where it is, what it senses, and whether it survives. 1 billion more miles feels much emptier when the craft has become mute. At that point, the journey no longer unfolds as a shared act of discovery. It unfolds as a physical fact that no longer includes us in the same way. And that is why the spacecraft begins to feel less like a Voyager in the ordinary human sense, and more like a preserved fragment from the 20th century. A cold machine from 1977, a body of metal, wire, insulation, and memory. A relic from the era of slide rules, magnetic tape, and early planetary exploration, still drifting through darkness long after its makers, operators, and audiences have disappeared. There is a kind of grandeur in that. There is also a kind of emptiness. The mission survives as trajectory. It survives as symbolism. It survives as hardware. It does not survive as an active act of exploration. So when people picture Voyager in the year 3000, what exactly are they picturing? A spacecraft, a message, a memorial, or simply a dead object from Earth, still moving through space because nothing has arrived to stop it? The moment the golden record enters the story, Voyager stops feeling like only a scientific instrument. It becomes a symbol. It becomes a message. It becomes a cultural artifact sealed onto the side of a machine that was already leaving home. The record itself is small enough to hold in 2 hands. It is a 12-inch gold-plated copper disc protected by an aluminum cover. Attached beside it are simple playback instructions, a cartridge, and diagrams meant to help an unknown finder understand how the record works. Those details matter because they shift the emotional meaning of the spacecraft. A camera or magnetometer feels technical. A record filled with sounds and images from Earth feels personal. The contents deepen that feeling. The record carries greetings in 55 languages. It carries 116 images encoded as analog signals. It carries about 90 minutes of music. It carries sounds from this planet, including thunder, wind, waves, birds, crickets, footsteps, laughter, a kiss, and a baby crying. It carries pieces of Bach, Beethoven, Mozart, Stravinsky, Chuck Berry, and music from several other cultures and traditions. It carries human anatomy, landscapes, animals, scientific diagrams, and scenes of ordinary life. A machine that studies Jupiter is one kind of object. A machine carrying all of that feels like something else entirely. It feels as though humanity paused for a moment in 1977, looked into the dark, and decided to leave a trace of itself there. That is why the Golden Record changes the story so strongly. Without it, Voyager can be understood as an extraordinary probe whose mission expanded because the hardware endured. With it, Voyager begins to feel like an intentional ambassador. It starts to feel less like a spacecraft and more like a gesture. That gesture was shaped very quickly. Carl Sagan led the committee that assembled the record, and the work happened under real-time pressure before launch. The team had only months, not years, to decide what represented Earth well enough to be bolted onto a spacecraft. That compressed timeline adds to the feeling that the record is not a complete portrait of humanity. It is a capsule, a compressed sample, a careful offering from one brief moment in late 20th century history. And because it is a message, people naturally imagine a receiver. They imagine a future intelligence finding Voyager. They imagine some distant mind decoding the diagrams, playing the record, hearing rain, hearing music, seeing the human form, and realizing that another civilization once lived on a small world orbiting an ordinary star. That imagined scene is powerful because it gives Voyager an ending. It turns endless outward motion into the possibility of recognition. It turns silence into delayed conversation. It turns a dead probe into a messenger that may one day complete its delivery. That is a deeply satisfying picture. It is also built on odds so poor that the symbolism becomes more powerful, not less. Space between stars is not crowded. Even in the local interstellar medium, the average density is about 1 atom per cubic centimeter. That is an almost perfect vacuum by human standards. The nearest star beyond our own system is more than 4 light-years away. Voyager is not heading toward a known inhabited world. It is not aiming for a planet. It is not steering toward a radio source. It is simply continuing along the path created by its last major gravitational slingshot at Saturn in 1980. That means the record does not ride on a realistic delivery route. It rides on endurance and hope. The practical chance of Voyager passing near another civilization is so small that the record works best, not as a likely communication device, but as a statement about the species that launched it. It tells us something about human beings in 1977. We were curious enough to study giant planets, sentimental enough to attach greetings and music, bold enough to imagine that even a nearly impossible message might still be worth sending. That is why the Golden Record gives Voyager so much of its emotional weight. It does not make the mission more useful in a practical sense. It makes the mission more human. And once that record is on board, it becomes much harder to think about Voyager as a silent machine drifting through cold distance. It starts to feel like a message, still waiting for its reader. But on the timescales people actually care about, Is there any realistic reader waiting at all? Carl Sagan described the golden record as a message in a bottle cast into the cosmic ocean. That image is beautiful because it is easy to picture. A small object leaves shore. It carries voices, music, and fragments of ordinary life. It drifts into darkness long after the people who released it are gone. On a beach or in a novel, a bottle like that might one day wash into someone else's hands. In interstellar space, the comparison becomes much harsher. The ocean is real, in the emotional sense, but it is far emptier than any ocean on Earth. Voyager 1 is a machine about the size of a small car. Its main dish antenna is 12 feet across. Its total mass at launch was about 825 kilograms, or about 1,820 pounds. That is tiny compared with the distances it is moving through. Even the nearest star beyond our own system is more than 4 light-years away. 1 light-year is about 5.88 trillion miles. That means the nearest stellar neighborhood is separated from us by tens of trillions of miles, and Voyager is not aimed at any known inhabited place within that distance. It is simply following the path created by planetary gravity assists decades ago. That matters. A bottle in the ocean at least drifts across a medium crowded with coastlines, currents, islands, ships, and living creatures. Voyager moves through a region where the average density of matter is so low that a cubic centimeter of interstellar space may contain only about 1 atom. Not 1 molecule of air, not a grain of sand, 1 atom. That is the practical emptiness behind the poetry. The record encourages people to imagine a future finder because that is what messages are for. Messages imply reception. They imply another listener. They imply a reply, even if the reply comes much later. But Voyager is not traveling through a busy corridor between civilizations. It is not approaching a planet that astronomers suspect might host technological life. It is not passing through the center of a known star cluster packed with worlds. It is moving through a vast region of sparse gas, dust, and darkness where almost everything is very far from everything else. Even if intelligent civilizations exist elsewhere in the galaxy, they would be spread across distances so extreme that detection alone would be difficult, and physically crossing paths with a small, silent spacecraft would be far harder still. That is why the chance of Voyager ever being found is so small. Not small in the ordinary sense, vanishingly small. The spacecraft is tiny. The galaxy is enormous. The Milky Way is about 100,000 light-years across. Voyager's path is just one narrow line inside that immensity. For another civilization to find it, that civilization would first have to exist, then exist near the path, then possess the technology to detect a cold, dark object only a few meters wide, then care enough to investigate it, then understand what it was. That chain is not impossible. It is just so unlikely that the record works best as a symbol rather than a practical instrument of contact. And yet the beauty does not disappear when the odds collapse. In some ways, it becomes sharper. The record carries greetings in 55 languages. It carries a mother and child, animals, landscapes, scientific diagrams, and music, chosen under the pressure of a real launch schedule in 1977. That means it is not just a message for others. It is also a message about us. It tells us what one group of human beings, in one brief moment of the 20th century, believed was worth preserving. Not our wars, not our arguments, not our stock markets or borders. Sounds of rain, music, laughter, the shape of DNA, the look of a human face. That is what makes the record moving. It is both grand and fragile. It speaks in the tone of a species that hopes to be found while knowing it almost certainly will not be. And when those two truths sit together, the story begins to change. The message remains beautiful. The space around it remains almost empty. The gesture remains human. The practical future remains brutally thin. If that is true, then the idea of Voyager as a meaningful interstellar messenger starts to feel less secure. It starts to feel like something we may have projected onto the mission after the fact. By the year 3000, Voyager's distance from Earth will sound impressive in conversation. It will still feel like a machine far out ahead of us. A lonely object deep in darkness, carrying the name of one of humanity's greatest missions. But practical usefulness is a different thing. A silent spacecraft cannot send measurements. It cannot aim its instruments. It cannot update its software. It cannot report damage. It cannot tell us what it sees. That limits what its distance can actually do for us. The most obvious limit is communication. Once Voyager falls silent in the late 2030s or early 2040s, its outward motion stops producing new scientific return. Its position may keep changing. Its scientific value does not keep growing in the same way. Distance by itself is not data. Data comes from instruments that still work, still point, and still talk back. Without that exchange, Voyager becomes physically farther and informationally quieter at the same time. That matters because astronomy does not depend only on traveling outward. It also depends on learning how to read light more carefully from where we already are. Long before the year 3000 arrives, humans will have gathered enormous amounts of information without sending a probe thousands of astronomical units away. Astronomers already study exoplanets by watching them pass in front of their stars. That method is called a transit. A transit slightly dims the starlight. From that tiny drop in brightness, scientists can estimate a planet's size, orbital period, and sometimes even its atmosphere. They also use spectroscopy, which means splitting light into its component colors and reading the chemical fingerprints hidden in that pattern. With spectroscopy, astronomers can detect gases such as water vapor, carbon dioxide, methane, sodium, and hydrogen in distant planetary atmospheres. That is remarkable. When you remember that some of those worlds are dozens, hundreds, or even thousands of light years away. A silent probe drifting a few thousand astronomical units from Earth does not automatically compete with that. The same is true closer to home. We have already mapped Jupiter, Saturn, Titan, Europa, Pluto, and many asteroids with later missions, better cameras, radar, infrared sensors, and more powerful computers. Ground-based observatories have mirrors measured in meters. Space telescopes avoid atmospheric blur. Radio telescopes can combine signals from many dishes spread across long distances to sharpen resolution. That technique is called interferometry. Instead of building one impossible giant telescope, astronomers let many smaller ones act together like parts of a much larger instrument. All of that means useful observation often comes from precision, sensitivity, and signal analysis, not simply from sending one object farther away. There is also the question of baseline. which is the separation between observing positions. A larger baseline can improve certain kinds of measurement, especially parallax, the tiny apparent shift in a nearby object when viewed from different locations. In theory, a probe very far from Earth could contribute to that kind of work. In practice, a dead probe cannot. A baseline only helps if the instrument at the far end is still alive, still calibrated, and still transmitting. Voyager in the year 3000 would offer distance without participation. And even if you imagine a future where humanity wants deep space observing platforms, it is hard to believe Voyager itself would remain the best tool for that job. It was built in the 1970s. Its onboard computer memory was measured in kilobytes. Its cameras were designed before the digital imaging revolution transformed nearly every part of astronomy. Its scientific payload was brilliant for its time and tiny by the standards of later generations. A civilization capable of building advanced observatories, laser communications, next-generation probes, or autonomous telescopes in the outer solar system would not depend on a mute artifact from 1977 for serious long-term science. That is the gap this section has been moving toward. Voyager's outward motion remains emotionally powerful. Its practical information yield does not keep rising with the same elegance. One grows in symbolism. The other stops when the signal stops. So, by the year 3000, the spacecraft may still inspire awe simply because it is out there. But awe and usefulness are not the same thing. And if distant observation already handles much of the work that matters, then what exactly was the long-term interstellar payoff supposed to be? There is a deeper reason Voyager starts to feel smaller once you follow it far enough into the future. The farther ahead you imagine human knowledge, the older Voyager begins to look. It launched in September 1977. Its computer memory was measured in kilobytes. Its cameras belonged to the late 20th century. Its power system began with about 470 watts, which is less electricity than many kitchen appliances use in a single moment. Its great strength was never that it was futuristic forever. Its great strength was that it kept working long enough to outlive the era that built it. That endurance matters. It deserves respect. But endurance and relevance are different things. A civilization living in the year 3000, or even a civilization only a few hundred years ahead of us, would likely have tools far beyond anything Voyager could offer. Think about what changed on Earth in only the past 300 years. In the early 1700s, there were no airplanes, no radio, no electricity grids, no photography, no antibiotics, no computers, and no rockets. By the early 2000s, humans had walked on the moon, mapped planets with robotic probes, split the atom, built global communication networks, and launched space telescopes that could analyze light from worlds orbiting other stars. That happened in a span shorter than the time Voyager needs just to reach the inner edge of the Oort Cloud. So, if a future civilization cares about nearby interstellar space, it probably will not depend on a silent machine from 1977 drifting outward on a path chosen during the Carter administration. It would build better instruments. It would launch faster probes. It would likely place active observatories far beyond Earth, with modern detectors, modern power systems, and communication methods far more efficient than a fading radio link across billions of miles. Even our own astronomy already points in that direction. We study exoplanets by reading tiny changes in starlight. We split that starlight into spectra and look for chemical fingerprints. We map asteroids with radar. We study the atmospheres of distant worlds without ever landing on them. We send newer probes with better imaging, better computing, and more specialized payloads than Voyager could have carried in the 1970s. That means Voyager's deep future begins to look less like the future itself, and more like an early draft of it. A brave draft, a beautiful draft, but still a draft. You can feel that most clearly when you imagine two different machines side by side. One is Voyager 1. It is a silent craft, built from aluminum and titanium, carrying a record, moving at about 17 kilometers per second, unable to steer in any meaningful modern sense, unable to observe for us once. Its power is gone. The other is some future probe built centuries from now. That future machine might use autonomous navigation, advanced sensors, miniaturized instruments, stronger onboard computing, and a propulsion system that makes Voyager's velocity look as limited as a steam engine looks beside a jet. The comparison is harsh. Voyager begins to resemble the Wright Flyer of interstellar symbolism. The Wright Flyer mattered enormously. It proved something real. It opened a door. But no one mistakes it for a modern aircraft. No one treats it as the vehicle that would still define aviation once aerodynamics, engines, materials, and navigation had matured. That is the role Voyager starts to occupy in this story. Less the finished expression of humanity reaching outward, more the first fragile proof that we had started trying. That shift changes the emotion of the mission. For decades, Voyager has been allowed to stand in the mind as a kind of permanent future object, a machine already representing humanity among the stars. But real futures tend to move past their first prototypes. If humans remain technologically active for even a few more centuries, they will almost certainly build outer system observatories, faster robotic craft, better communication systems, and much more deliberate interstellar missions. Those later efforts would do with intention what Voyager does only by persistence. And once that becomes clear, the mythology around Voyager begins to wobble. Its scientific achievements remain secure. Its symbolic value remains powerful, but the larger story people tell, the idea that Voyager itself is meaningfully carrying humanity into the interstellar future, starts to feel exaggerated. At that point, the harsher framing moves into view. The engineering was brilliant. The mission was historic. But was the interstellar mythology around Voyager partly a mistake? This is where the harsher reading enters. If Voyager is treated as a meaningful path toward interstellar contact or practical exploration, the picture starts to break down. The language around the mission often sounds enormous. Humanity reached the stars. Humanity sent its first ambassador into the galaxy. Humanity began its journey beyond the solar system. Those phrases carry real emotional force. They also suggest a level of physical progress that the actual numbers do not support. By the year 3000, Voyager will have been traveling for a little more than 1,000 years. That sounds like an age. On the real map, it places the spacecraft near the beginning of the Oort Cloud, the huge outer swarm of icy bodies that still belongs to our star's wider gravitational domain. The inner edge of that region is often placed around 2,000 astronomical units away. That is about 186 billion miles. Crossing the whole Oort Cloud may take around 30,000 years. So the year 3000 does not place Voyager deep into a meaningful interstellar future. It places Voyager at the opening stretch of the solar system's farthest debris field. That is a very different image. It is one thing to say Voyager became the first human-made object to enter interstellar space in 2012, meaning it crossed the heliopause and moved beyond the region dominated by the solar wind. That is true. It is another thing to let that phrase swell into the idea that Voyager is effectively on its way to another civilization, another world, or some practical new frontier. That is where the interpretation begins to overreach. The spacecraft is silent by then. Its instruments are dead. Its cameras are dead. Its power is gone. Its distance from Earth is huge by human standards and still tiny compared with the scales people associate with star travel. That is why the word mistake begins to appear. The engineering was not a mistake. The science was not a mistake. The Jupiter flyby in 1979 was not a mistake. The Saturn flyby in 1980 was not a mistake. The close pass by Titan was not a mistake. The decades of data returning from deep space were not a mistake. What starts to look mistaken is the mythology layered on top of those achievements. The mythology says outward motion equals interstellar progress. The mythology says a machine carrying a golden record is somehow moving toward contact in a meaningful human sense. The mythology says that enough time turns drift into destination. The year 3000 strips that mythology down to scale. It shows a spacecraft still near home by the standards that matter here. It shows a mission that became symbolically larger and physically smaller at the same time. The symbol grew. The practical reach did not grow with it. That gap matters, because once people hear Voyager described as humanity reaching the stars, they absorb a picture that feels more advanced than reality. They picture a road already underway. They picture the first chapter of a true interstellar story. What the Oort Cloud timescale reveals is something much more limited and much more honest. Voyager was a brilliant planetary mission that happened to continue outward long enough for human beings to project a larger meaning onto it. That larger meaning feels inspiring. It also risks confusing persistence with progress. A bottle drifting farther from shore is still drifting. A relic moving through darkness is still a relic. A spacecraft launched in 1977 remains what it was, even after the calendar marches forward for 1,000 years. And once that is fully faced, the sharper version of the argument becomes hard to avoid. Voyager may have been treated as the beginning of humanity's journey to the stars. What it may actually represent is the beginning of humanity's realization that the stars are far harder to reach than our language likes to admit. That is where the accusation lands. Mistake belongs to the interpretation. Mistake belongs to the emotional inflation. Mistake belongs to the story we told ourselves about what this machine meant once it kept surviving. Even so, that accusation only holds together if we stay just as honest about the reason the word still feels unfair. The word mistake lands hard because it pushes against something real. Voyager 1 was one of the great engineering achievements of the 20th century. It launched from Cape Canaveral on the 5th of September 1977. Its twin, Voyager 2, had launched a little earlier on the 20th of August 1977. Together, they were built to survive cold, radiation, distance, and long communication delays with hardware designed in an era before laptops, smartphones, and modern digital imaging. Voyager 1 carried about 69 kilobytes of computer memory. That is less memory than a short email draft with a photo attachment. Its power system began with roughly 470 watts from a radioisotope thermoelectric generator. Its main dish measured about 12 feet across. Its total launch mass was about 1,820 pounds. Those numbers feel small now. That is part of what makes the mission impressive. A machine with that kind of hardware reached Jupiter in March 1979 and Saturn in November 1980. It photographed storms, rings, moons, and atmospheres in detail that had never been seen before. It helped reveal active volcanism on Io. It gave scientists new views of Europa's cracked ice. It showed Saturn's rings as a dynamic structure made of countless particles and narrow ringlets rather than a smooth decorative band. It helped establish Titan as one of the most intriguing moons in the solar system. Those were not side benefits. That was mission-defining science. And then the spacecraft kept going. That may be the part that makes the word mistake feel most unfair. Voyager did far more than almost anyone had a right to expect. NASA originally planned a mission measured in years. Instead, Voyager remained active for decades. It crossed the heliopause in August 2012 and became the first human-made object to enter interstellar space in the plasma and particle sense. That milestone was historic. Even the long delay in communication became part of its achievement. By the time Voyager crossed that boundary, radio signals took about 17 hours to travel one way between the spacecraft and Earth. A command sent from Earth took most of a day to arrive. A reply took most of another day to come back. That kind of distance is real. That kind of persistence is real. The mission also succeeded emotionally. That matters too. Voyager became a symbol because it earned the right to become one. It carried a golden record with sounds, greetings, and music from Earth. It endured long enough for people to feel that it represented more than engineering. A machine that dies after a short technical mission does not gather that kind of meaning. Voyager did. It survived long enough to become part of humanity's larger self-image. That is why the critique has to stay narrow. The critique cannot be that Voyager failed. It did not fail. The critique cannot be that Voyager was badly engineered. It was engineered brilliantly. The critique cannot be that sending it outward had no value. It had enormous value. What is under pressure here is something more specific. It is the way people later talked about what that survival meant. It is the way a planetary mission became inflated into a practical interstellar beginning. That difference matters because a mission can be historic and still be misunderstood. The Wright Flyer was historic. It also would not function as a modern passenger aircraft. The first transatlantic telegraph cable was historic. It also did not make later communication technology unnecessary. Early achievements often deserve admiration without being mistaken for fully formed versions of the future. Voyager belongs in that category. It was a first great outward step. It was also a machine with clear limits, tied to the science, hardware, and velocities of its era. That is why mistake feels too cruel. The word threatens to flatten the mission into a failure when the mission was anything but that. It risks punishing Voyager for the scale of the universe rather than crediting it for what it actually accomplished inside that scale. So the tension now needs a cleaner boundary. Voyager can be an extraordinary scientific success. Voyager can also be a poor model for what meaningful interstellar usefulness really looks like. To move forward honestly, those two ideas need to be separated. Voyager becomes easier to understand once the two versions of the mission are pulled apart and placed side by side. The first version is the real historical mission. The spacecraft launched in 1977. It used a rare outer planet alignment and a chain of gravity assists to reach Jupiter in 1979 and Saturn in 1980. It returned thousands of images and measurements that changed planetary science. It revealed active volcanoes on Io, strange cracked ice on Europa, complex ring structure around Saturn, and a thick nitrogen atmosphere around Titan. On those terms, Voyager was a triumph. A machine built with 1,970s electronics crossed billions of miles, survived intense radiation, stayed in contact with Earth for decades, and kept working far beyond its expected lifetime. That version of Voyager deserves almost every word of praise it has received. Then there is the second version. This is the one that formed slowly afterward. The probe kept moving. It crossed the heliopause in 2012. It carried a golden record. It became the most distant, human-made object ever built. Those facts gathered emotional weight year after year until a new story formed around them. Voyager stopped feeling like a planetary mission that continued outward. It started feeling like humanity's first real voyage to the stars. That second version is powerful. It is also where the scale problem begins. As a practical interstellar project, Voyager is frail. Its power fades within decades, not millennia. Its instruments go silent long before it reaches the inner edge of the Oort Cloud. Its speed, about 17 kilometers per second, is extraordinary for a robotic probe and painfully small against stellar distances. Its path does not lead to a known habitable world, a nearby star system, or a realistic site of future contact. Its golden record is moving as a symbol and nearly powerless as a practical communication tool. That does not erase the first truth. It sharpens the second one. Voyager succeeded brilliantly at one job. People later imagined it succeeding at a different one. Those are separate claims. The mission that studied Jupiter and Saturn was robust, deliberate, and scientifically transformative. The image of Voyager as a meaningful bridge to interstellar contact is far thinner. By the year 3000, that difference becomes impossible to ignore. The real mission will be long over. The spacecraft will have been silent for centuries. The probe will still be near the beginning of the Oort Cloud on the larger gravitational map. That means the symbolic version of Voyager grows larger in the imagination at exactly the point where the practical version grows smaller. One becomes legend. The other becomes limitation. A helpful comparison is early flight. The Wright Flyer in 1903 was a breakthrough. It proved controlled powered flight was possible. It stayed in the air for only seconds at a time and traveled a distance shorter than the wingspan of a modern passenger jet. No serious person would look at that machine and say it was already practical global aviation, but everyone would rightly say it mattered. Voyager occupies a similar place. It proved that a human-made machine could go farther than any before it, survive for decades, cross into interstellar space in one physical sense, and carry part of Earth outward. That matters deeply. It also does not mean the spacecraft became a practical interstellar explorer in the fuller sense people often imply. That is where futility enters the story. Not total futility, not scientific futility, not engineering futility, futility on a narrower and colder level. If the imagined goal is active interstellar usefulness, meaningful future observation, likely contact, or a serious pathway toward the stars, Voyager falls short by an enormous margin. It keeps moving. It does not keep doing very much. That distinction is the center of the whole script. Voyager was magnificent. As an outward-looking planetary mission, Voyager was fragile and limited as a practical interstellar gesture. Both statements can remain true at the same time, and once they are kept separate, the year 3000 stops sounding like a distant celebration and starts sounding like a measurement of how far the spacecraft has gone, a measurement of how little that changes on the real cosmic map, and above all, a measurement of how easily human beings confuse survival with arrival. What the year 3000 really exposes is not a flaw in Voyager alone. It exposes a flaw in us. Human intuition was built for hills, coastlines, storms, seasons, and journeys that fit inside one lifetime. It was not built for a spacecraft leaving Earth in 1977 and still remaining close to home by cosmic standards more than 1,000 years later. That is why the date feels so deceptive. 1,000 years is enough time for the political map of Earth to be redrawn beyond recognition. In the year 1000, William the Conqueror had not invaded England yet. The Song dynasty ruled in China. The printing press did not exist in Europe. There were no telescopes, no engines, no electricity grids, no radio, no aircraft, and no satellites. From there to now, human beings built cathedrals, empires, factories, railroads, telegraphs, nuclear reactors, microchips, and space probes. That is what 1,000 years feels like in human history. It feels total. It feels like more than enough time for a mission to become destiny. Then, space imposes its own scale. Voyager crosses the heliopause in 2012. That sounds final. Voyager reaches the inner edge of the Oort Cloud only after roughly 300 years of travel. Crossing that distant cloud may take around 30,000 years. Set those numbers beside the year 3000 and the emotional balance changes immediately. The calendar surges forward. The spacecraft barely changes chapters. That contrast is the real force of this thought experiment. The date sounds medieval and distant. The physics sound unfinished. That gap tells us something important. It tells us that human beings are very good at feeling the weight of time and very poor at feeling the weight of distance. We hear 1,000. We picture completion. We hear interstellar. We picture progress toward a star. We hear most distant human-made object. We picture a machine already deep into the future. The actual machine is quieter and harsher than that. It moves at about 17 kilometers per second. Its power fades within decades. Its instruments die on a normal historical timeline. Its outward motion continues. But its practical role collapses long before the year 3000 arrives. That is where symbolism begins to outrun hardware. The more famous a mission becomes, the easier it is for its meaning to expand faster than its physical reach. Voyager studied Jupiter and Saturn with extraordinary success. Then it endured. Then it crossed a historic boundary. Then it carried a golden record. Each of those facts is real. Together, they generated a much larger myth. The myth says that humanity already has a hand extended meaningfully into the stellar dark. The hardware says something smaller. It says that our first outward gesture was brave, ingenious, and painfully limited. That difference does not make Voyager ridiculous. It makes Voyager revealing. A famous mission can become a mirror. People begin by looking at the spacecraft. Then, without noticing, they start seeing their own hopes reflected in it. Hope for contact, hope for continuity, hope that sending something outward is almost the same as beginning to arrive somewhere. The year 3000 strips away some of that comforting blur. It leaves the dates in place. It leaves the distances in place. It leaves the dead hardware in place. And once those pieces are held together long enough, the real meaning of Voyager starts to shift. The mission stops looking like a shortcut to the stars. It starts looking like humanity's first honest lesson in how hard the stars truly are. That is a more mature kind of meaning, a harder kind, also a more valuable one, because the point no longer rests on whether Voyager fulfilled every story later attached to it. The point rests on what Voyager teaches, once the romance and the arithmetic are allowed to stand side by side. And that makes the final interpretation feel less like an attack on the mission and more like an attempt to understand what the mission has really been saying all along. Voyager may matter most here because it shows how thin our first outward gesture really was. For decades, it has been easy to speak about Voyager in heroic language. The first craft to leave the solar system. The first craft headed toward the stars. The first ambassador of Earth. Those phrases carry real emotional force because the mission truly was historic. Voyager 1 launched in 1977. It crossed the heliopause in 2012. It became the most distant human-made object ever built. All of that remains true, but the year 3000 changes the emotional balance. It keeps the grandeur. It removes the illusion of scale. 1,000 years from launch sounds like the kind of interval that should transform everything. It is longer than the gap between us and the Norman conquest of England. It is longer than the rise and fall of many kingdoms. It is long enough for languages to drift, coastlines to change, and entire belief systems to split into forms their founders would no longer recognize. And yet, after all of that human time, Voyager is still only beginning the Oort Cloud. That is the humbling part. The machine keeps moving. History keeps collapsing and rebuilding behind it. The larger picture barely changes. That is why Voyager starts to feel less like a victorious reach into the galaxy and more like a lesson in proportion. Human beings built a machine with a 1-2 foot dish, a few hundred watts of power, and 1,970s electronics. They sent it past Jupiter and Saturn with remarkable precision. Then they watched it continue into darkness. That achievement is beautiful. It is also very small against the actual architecture of space. There is a kind of honesty in that. Voyager does not flatter us once you follow the numbers far enough. It does not confirm that humanity has already begun to conquer interstellar distance in any practical sense. It confirms that our first real outward motion was brave, intelligent, and tiny. That does not make the mission empty. It gives the mission a different kind of dignity. A child's first step is tiny. A first bridge across a river is narrow. A first ship leaving sight of land is fragile. Voyager belongs to that category. It is moving proof that we began. It is also proof of how little beginning actually accomplishes when the scale is this large. That is where the loneliness enters more fully. Voyager will be silent long before the year 3000 arrives. Its instruments will have stopped working. Its final signal will be centuries in the past. No one alive then will hear a fresh report from that craft. What remains is a cold object from 1977, drifting through a region so large that human history barely scratches it. The golden record deepens that feeling. It carries music, greetings, images, and sounds from Earth. It turns the spacecraft into something personal. But once the practical odds are faced honestly, the record feels less like a likely act of contact and more like a quiet act of testimony. We were here. We built this. We wanted to reach outward, even before we truly understood how hard that outward reach would be. That is why Voyager ends up feeling poignant rather than triumphant. It is still heroic. It is still one of the greatest missions humanity ever carried out. But the deepest meaning may be gentler and sadder than the mythology first suggests. Voyager was not our arrival among the stars. Voyager was our first honest encounter with how far away the stars really are. That is a different kind of greatness, a more mature kind, a greatness measured less by conquest and more by clarity. Because once that truth settles in, the sharper language from earlier begins to soften. The mission itself no longer looks like the target. What comes into view instead is the human need to turn every first gesture into a larger story than the hardware can actually support. And that leaves only one thing left to settle. Was Voyager a mistake? Or was it something much more revealing than that? By this point, the word mistake has done its work. It has forced the mission into a harder light. It has stripped away some of the warm mythology that gathered around Voyager after 1977. It has made the year 3000 feel less like a triumphal destination and more like a scale test that humanity fails almost immediately. But now the question has to become more precise. What exactly was mistaken? Was the mission itself wrong? Or was the misunderstanding ours? Voyager 1 was built to do something very specific. It was built to fly past Jupiter and Saturn, return close-up science, exploit a rare planetary alignment, and survive long enough to extend that success outward. On those terms, it succeeded almost beyond belief. It reached Jupiter in March of 1979. It reached Saturn in November of 1980. It helped reveal active volcanoes on Io, deep complexity in Saturn's rings, and the strange atmospheric chemistry of Titan. It remained alive for decades longer than anyone could confidently expect from a machine launched in the 1970s. It crossed the heliopause in 2012. None of that looks like failure. None of that sounds like a mistake. The discomfort enters only when later generations begin asking the spacecraft to symbolize more than it was ever physically capable of achieving. A planetary mission becomes a star-bound legend. A drifting probe becomes a practical emissary. A golden record becomes a message that feels as though it must somehow matter on reachable timescales. That is where the distortion begins. And that distortion tells us something important. Human beings do not merely measure distance. They narrate it. They turn motion into destiny. They turn endurance into arrival. They turn a surviving object into a promise about the future. Voyager exposed how easily we do that. It exposed how quickly symbolism can outrun physics. It exposed how a machine can remain admirable, while the story built around it grows larger than the hardware can honestly support. That is why the deeper lesson may have less to do with Voyager's limitations and more to do with ours. We are a species that evolved in landscapes where horizons were near, journeys ended, and effort usually produced visible progress. Walk long enough, and you reach the next valley. Sail far enough, and you reach another shore. Build a stronger ship, and the world opens a little more. Space does not obey that emotional logic. The nearest star sits more than 4 light-years away. The Oort Cloud may extend to nearly 2 light-years from our own star. Voyager can travel for 1,000 years and still remain close to home by cosmic standards. That is not a defect in the spacecraft. That is a revelation about the universe. In that sense, Voyager may have achieved something more unsettling than the mythology first promised. It forced humanity into its first honest encounter with cosmic disproportion. It showed that our first outward reach was real and also incredibly thin. It showed that interstellar language comes easily, while interstellar usefulness comes far more slowly. It showed that a mission can be both magnificent and small. That is a difficult combination for people to hold in place. We like clear categories: success or failure, triumph or futility, beginning or arrival. Voyager refuses those easy divisions. It was a triumph as engineering. It was a triumph as planetary science. It was a triumph as a cultural symbol. It was also a very limited, practical gesture toward the actual distances between stars. Holding those truths together produces the strange emotional tone this mission leaves behind. Admiration remains. So does discomfort. The admiration comes from what human beings built and accomplished with modest hardware, finite power, and extraordinary care. The discomfort comes from realizing how little even that accomplishment changes once the scale expands to the size it always had. So perhaps the mission was not wrong. Perhaps the scale was the lesson. Perhaps Voyager's greatest achievement was never that it meaningfully carried us to the stars. Perhaps its greatest achievement was forcing us to feel, in a way numbers alone rarely can, how far away the stars really are. And if that is true, then the final answer has to preserve every part of that tension at once. Voyager 1 was launched on the 5th of September 1977 from Cape Canaveral, carrying cameras, spectrometers, a 1-2-foot dish antenna, and a power supply that began at about 470 watts. It reached Jupiter in March of 1979 and Saturn in November of 1980. It revealed volcanoes on Io, fine structure in Saturn's rings, and a thick nitrogen atmosphere around Titan. It crossed the heliopause in August of 2012 and became the first human-made object to enter interstellar space in that physical sense. Those are the facts of a legendary mission. They remain extraordinary, no matter how far forward the calendar moves. By every normal standard of science, engineering, and human ambition, Voyager was a success of the highest order. It worked far longer than its builders could safely promise. It kept sending data across billions of miles. It turned distant points of light into real places with storms, radiation belts, ice, methane haze, and volcanic fire. It also carried something stranger than data. It carried a golden record with music, greetings, images, and sounds from Earth. That record gave the mission emotional weight far beyond planetary science. It helped turn Voyager into a symbol of humanity reaching outward. That symbol still carries real beauty. The year 3000 leaves that beauty in place and changes its scale. A little more than 1,000 years after launch, Voyager will still be near the beginning of the Oort Cloud, the vast outer swarm of icy debris that may extend nearly 2 light-years from our star. Reaching the inner edge of that region takes about 300 years. Crossing the larger cloud may take around 30,000 years. That means the spacecraft's first great outward motion remains very close to home on the real cosmic map. Its active mission ends even earlier. Voyager's radioisotope power source fades on a normal historical timeline. The last signal is expected in the late 2030s or early 2040s, long before the year 3000 arrives. The probe becomes a cold artifact from the 1970s. Still moving, still real, still carrying its record, and no longer participating in any living exchange with Earth. That is where the harsher framing earns its place. The mission was legendary. The drift remains unfinished. Those truths live together. They do not cancel each other. Voyager deserves admiration because it did exactly what a great first mission should do. It proved that a human-made machine could survive the outer planets, endure decades in deep space, and keep going farther than anything before it. It also revealed how little that first gesture truly reaches once the scale expands beyond the planetary realm. In that sense, the word mistake belongs less to the spacecraft than to the story people later wrapped around it. The engineering was brilliant. The science was transformative. The mythology stretched farther than the hardware ever could. That is a very human thing to do. We turn motion into destiny. We turn endurance into arrival. We turn a surviving object into a promise. Voyager gently resists all of that. It keeps the romance and restores the proportions. It says that our first step into the cosmic dark was real, brave, and astonishingly small. That may be the mission's deepest legacy. Voyager did not carry humanity meaningfully toward another star on a timescale people can feel as practical. Voyager carried humanity into its first honest confrontation with how vast the universe really is. That lesson matters. It matters because every later mission will be judged against it. Every future probe, observatory, laser sail, fusion craft, or true interstellar attempt will begin with the scale Voyager helped expose. The spacecraft becomes a threshold in that way, a first outward mark, a first proof of intent, a first admission that the distance between stars does not shrink just because our stories want it to. So was Voyager a mistake? As science, no. As engineering, no. As a human act of curiosity, no. As a reminder of how easily we exaggerate our first reach into the universe, maybe yes. And perhaps that is the most honest answer this mission can give us. Voyager was a triumph. Voyager was a symbol. Voyager was a relic in the making. Voyager was our first small step into a darkness so large that even 1,000 years barely changes the view. If that feels humbling, it should. That humility may be the most valuable thing Voyager leaves behind.